Hello everybody, welcome back to our journey through parallel C++ and scientific computing. What I want to do today is to start actually looking at some methods how scientific computing is done. And one of those methods is called the Monte Carlo method. It got its name from a very small place in Europe on the coast of the Mediterranean Sea in France. It's actually a beautiful place. I've never been there. I can't afford going there. It's, you can compare it to the Las Vegas of Europe. It's famous for its big casino and for the very wealthy people that congregate there. So Monte Carlo, if ever you want to go there, just you have to kind of first create a big company and use C++ for something useful, and then you will be able to go there. But the name Monte Carlo methods comes from that casino, because casino is, as you know, something very random. And Monte Carlo methods rely on random numbers. It's essentially a method of applying randomness to scientific problems and calculating averages afterwards, so that you can estimate the result if there's no other way of doing that. So let's start. Since computers can't really have random numbers, well, they can, but it's very expensive to generate those. What we do in computers, we use so-called pseudo-random numbers. And the simplest way to generate a pseudo-random number is a famous comic. Get random number, return 4, and just add a comment to it that I chose that 4 by rolling a fair dice. This is definitely a random number generator. It just has the disadvantage that it always generates the same number. But hey, it's random, right? For our purposes, where we want to generate a large amount of random numbers, this is certainly not applicable. So let's have a look at what we can do in C++ to really generate sequences of random numbers. These pseudo-random numbers that are used in computing are essentially deterministic sequences of numbers. Deterministic in the sense that they will always come in the same sequence when you start generating them. On each invocation of the function, the function will return a new number. But if you start your application over and over again, it will generate the same sequence of numbers. But the sequence of those numbers have certain statistical properties so that they are uniformly distributed or have a normal distribution or whatever you desire. So what you want to have for these random numbers sequences is that they have a possibly very long period, because at some point the random number generators will start from the beginning and will start generating the same numbers over again. You want for them to be efficient because, well, if you want to generate millions or billions of random numbers, you don't want to have to wait for a second to generate a new one. It has to be repeatable if you want to, just for testing purposes, for reproducibility, so you can diagnose problems or things like that. On the other hand, you want to be able to generate different numbers each time you run it. So you want to have the choice to do either or. And last but not least, these random number generators should be portable so that you can get the same results when you run it on a Mac or on Windows or on Linux or on other systems. So in the simplest example, let's say I have a sequence of numbers which I calculate from A times the previous number plus B, do a modulus division. That will give me certain random numbers, especially when I choose the constants in a very careful way. What we will get are numbers that are in the range between 0 and C, because we have that modular division there. But unfortunately, this is not really suitable for really statistically properly distributed numbers, because the correlation between the numbers is too large. So people do other things. But let's assume we have a generator that gives us a random number between 0 and a certain upper constant, and these numbers are evenly, uniformly distributed in between those. Then we certainly can get, for instance, floating point numbers in a range of 0 to 1 just by divide the integers by c plus 1, and that gives us a floating point number in the range between 0 and 1. If you want to get integers in a range between u and v, we just apply a certain other mathematical, very simple conversion, which will give us a evenly distributed sequence of numbers in between u and v. Luckily, in C++, we don't have to create our random number generators ourselves. What we can do, we can rely on a library that is standardized and that is really conforming to all those requirements that are listed. They're very efficient. They have very nice statistical properties. And the best thing of all is that in C++, in the library, you have a separation of generating the numbers and creating the distribution. So you can use the very well-designed random number generators from the library and even can create your own distribution if you want to and combine that. Examples for these distributions are uniform integer distributions, uniform real or floating point distributions, normal distributions, whatever. So there are a whole set of these distributions that are available to you. Let's start with how you shouldn't do it. Well, that's a very simple example which calls a function which is called rand, and you might be familiar with that function, which comes from the C library and has been inherited from C. And you can just call rand, and it is supposed to give you a random number between 0 and a constant, which is rand underscore max, which is defined by the library. And while that will work well, and you will get a reasonably nice random number, there are problems with that. The other thing that is important to remember when you talk about random number generators is that on one hand you want to be able to guarantee that consecutive invocations of rand give you the same numbers when you run your application more than once. On the other hand, you might want for the numbers to be different. And for that, these random number generators have what's called a seed. So you seed them with a some number using the function srand. And what you can do just to seed it with some randomness, you seed it with the current time. You say, okay, the current time is my seed, and the random number generator will generate different sequences depending on the seed. That allows you to introduce pseudo-randomness into the sequence of numbers. On the other hand, if you call srand with the same constant every time, you get the same sequence. The reason why you shouldn't use these two functions is, well, we want to do parallel computing, and rand is not guaranteed to be thread safe. So if you use std_rand in a parallel environment, you might get unexpected results and everything but a random number. That's why don't do this. I know that people like doing that because it's simple and straightforward. In a parallel context, don't do that. How should you do it instead? Well, C++ gives you what's called a random device. It's in the standard namespace. You have to include the random header file. And the random device is a real random number generator. It looks at the temperature, at the, tilt of your device, at the position of the mouse, at the current time, at all kind of different really arbitrary values to generate a random number, which is real random. So we will use that to seed our random number generator. MT19937, that strange name, is actually one of the best generators you can get in the C++ library. It relies on the Mersenne Twister engine. You can read up on that. And you initialize it with a random number generated from our random device. You generate numbers by invoking the device. You just say, okay, RD, invoke it. It gives you that random number. And that random number is used as a seed for that Mersenne Twister engine. Okay, you might ask, why not use random device for every random number? It's very expensive. It's a very expensive call. You want to use it once. You want to use it only to produce a seed for a faster and more reliable, more efficient random number generator. Okay, now we have a generator and we create an integer distribution which is supposed to give us numbers between 1 and 6, or we generate a real distribution, uniform distribution that should give us numbers between 1.0 and 6.0. And now comes the trick. How do you use that? Well, you use just your distribution and pass to it the generator you want to use. And it will generate the random number based on the distribution. So this invoked with a generator will give you the integer, and this d, which is our double distribution, invoked with a generator will give us a floating point random number in that range. Very simple to use, and those things are thread safe and are safe to use in parallel environments. So I will, in the rest of the lecture, I will completely rely on these functionalities, and I will never go back to the srand and rand function I mentioned in the beginning. Okay. Since in the last lecture we talked about creating regular types, I introduced the singleton one, and I introduced the instrumented type. So I thought, why not use what we developed last time and create a histogram class, a type that represents a histogram. Does everybody know what a histogram is? A statistical. Who doesn't know what a histogram is? Do I have to explain that, or is that? Okay. You don't know what it is? Okay. Let's say you throw dice, okay? And you create a table where you count how often you throw these numbers, and so on. And you do it 1,000,000 times. So you get some counters for each of the values, and you can graph that. You can say, okay, 1, 2, 3, 4, 5, 6. And you will probably get something like this, because we assume that it's randomly distributed, so you probably get roughly the same amount of results. That graph is called a histogram. It's just a frequency plot of values. Now, if you have discrete values, this is simple, but you can use histograms also to represent buckets. So you measure something, and then you classify your results in ranges of values, which allow you to get a distribution of things. Okay? So what I thought is to create a class which is a regular class or a semi-regular class, which allows us to do that in code if you want to collect a histogram. So let's do that quickly. Has nothing to do with Monte Carlo methods, but I wanted to show you that the random number generators we have really create proper statistical distributions. And by that, I will collect histograms for a uniform distribution and for a normal distribution, and we will see that it really gives us what we expect. Okay, what do we need? When I want to create a histogram, what do I have to store in that histogram type? If I ask you to create a type that represents a histogram, what would you add as data members? Well, you obviously need the counts for a certain amount of counters, one counter for each bucket, and you want to have, well, one counter for each bucket. So in the simplest case, it's probably a vector of counters. And also, you want to store what is the minimum value and what is the maximum value I want to consider inside the histogram, because, well, you might want to discard kind of outliers or things like that. Okay? What else do we need if you want to create a regular class or a semi-regular class? We said last time, semi-regular classes need a copy constructor, copy assignment, and a destructor. That's the three things we need. Well, we got lucky, because we don't have to define them. The compiler-generated functions are just fine in our case, because the compiler-generated function apply its functionality to all members, and those members have well-defined semi-regular classes themselves, so we are good. We don't have to define those. But what we need is a constructor that allows us to initialize our histogram. And when we want to initialize a histogram, we need, well, probably 3 different values. We want to tell the histogram how many buckets to collect, what's the minimum value, and what's the maximum value to consider. What this class will do, it will actually collect num plus 2 buckets and will put everything that's lower or smaller than min value into one bucket and everything that's larger outside on the right side in a different bucket, so that we can count those if you want to as well. What we also probably need is a function that is called, I called add value, which just adds a value to the histogram. And what this will do, it will take the value and will increment the corresponding counter that corresponds to the bucket the value belongs into. So min value to max value divided by the amount of buckets. And then it will find which of the buckets actually I have to increment, right, to get my counter incremented depending on the value I have. And I will show the code for that, just to introduce what it's doing. And last but not least, I want to, in the end, once I have collected my histogram, what I need is 2 pieces of information. I need a list of midpoint values of the buckets, so I can draw a graph. And I want to have possibly normalized values of all counters. Normalized because that will allow me to nicely draw things, right? I just find the maximum value of all buckets and divide everything by that value and get something between 0 and 1 for the normalized data. Okay, let's have a look at that. So let's start with the constructor. And I will use that also to explain some of the C++ features while we go. Because this is about C++, not everybody knows C++ so well. That's why I want to kind of use all these examples to introduce you to different features of C++ as we go. So we have the 3 arguments, and what we need to do, we need to initialize the members in the constructor, because that's what constructor does. Remember, constructor is a function that is being called when a new instance of that variable is being defined. So we pass 3 values, we initialize our bucket data, and tell the vector you need num buckets plus 2 counters. And we just store the smallest and the largest value because we will need to calculate them later on. The syntax is a bit strange. You might think, what is this? This is outside of the body, right? It's a colon, then you initialize your members, and only then the constructor body is defined. This is how you do it in C++, because you want to be sure that inside the body the class is completely initialized. So you can do additional things if you want to. So all the members are usually initialized in the so-called member initializer list. And the syntax is like that. Colon, and then a comma-separated list of initializations for each of the members. Please interrupt me or ask questions if something is unclear or you would like to have more explanations. So let's look at add value. This thing adds 1 value to the bucket, so its task is to increment one of the counters in the vector of buckets. In the end, we have to calculate which index to use, and we have to increment that one element in that counter that corresponds to that index in our list of buckets. So how do we calculate the index? Well, the index is very, very simple. We will assume that index 0 corresponds to the values lower than the minimum, and the last bucket entry will correspond to the entries that are larger than the maximum. That's why by default, it will just initialize everything that's smaller, and we have to handle all the cases, all the other cases. So if the value is larger than max value, we have to do one thing, and if the value is larger than min value, otherwise, we have to place it in the correct bucket. So if it's larger than max value, we just initialize index to the index of the last element in our buckets. And otherwise, we do some calculations to find which of the buckets to use, just by dividing the max minus min value divided by the number of buckets, and then use that as the size of one bucket, and then use that to figure out which of the buckets we actually need. Okay? Not difficult, might not be obvious when you just look at it for 10 seconds, but it's really simple. In the end, it finds the correct index to increment the correct counter depending on the value I passed in to add value. Okay, so let's return the buckets, the midpoints of the buckets. What we need to do, we need to create a new vector which will be returned, and then first push back the minimal value in the first element, then have a loop which calculates the midpoints of all buckets, right? The delta is the size of one bucket, so the midpoints are the min value plus I times delta plus half of the delta, which gives us the midpoints of our buckets. And the last entry in the buckets is the maximum value, so that we can draw them correctly afterwards. Questions about that? The code is in the repository, so you can experiment with it, can look at it, can play with it. Last but not least, normalized data. And that one is a bit more interesting, because what I have to do in order to get a list of normalized data, I first have to find the maximum value, and then I have to divide all my values by that maximum value to get something in between 0 and 1. Well, I haven't talked about C++ standard algorithms a lot, and we will talk about that a lot over the semester. For now, we have seen two algorithms, right? We have seen for each, no, reduce, and we have seen unique. Max element is another one of those algorithms which goes over a sequence between the first and the second argument, which is the begin and the end of our buckets, and finds the maximum element, these things that are stored in that sequence. And I'm sorry for that. Not sure what's happening. I apologize for that. Okay. And it returns not the maximum value, but it returns essentially think about it as a reference to the element that is the maximum one. So max represents the maximum element in that sequence. Now we use transform, which is yet another algorithm. What transform does, it goes over the sequence I give it and applies a function to each element and puts whatever that function returns into an output sequence. That's what we do. We go over the bucket data. We put whatever it produces into our data vector we want to return. And here is a function. Let's not worry about the syntax for now. We will talk about lambdas and these functions in C++ in detail. Sorry for that. Don't know why Zoom is playing up today. And essentially what this does, it applies this piece of math to each element. So it takes the current element, divides it by the maximum value, and puts whatever it produces into the output. So you see that we could have done that with two loops, right? We could have written one loop that finds the maximum, another loop that actually does a calculation. But it's much more expressive to use the standard algorithms because A, you don't have to worry about loop boundaries. How often have you gotten your loop boundaries wrong when you wrote a for loop? Everybody has gotten the loop boundaries wrong once. These algorithms prevent you from making that mistake. And they actually tell you what the loop is doing without you having to look at the details, right? When you have two loops, you have to first understand what the hell is this loop doing. Here you see, okay, I get the maximum element, and then I transform my input sequence into some output sequence done. Okay, so this gives us the normalized data. Now let's use the histogram class for something useful. I just want to call it many, many times. I create a histogram and I say, okay, my histogram should have 100 buckets and should collect values between 0 and 1. Then I have a loop which adds a bunch of random numbers to that histogram. I will show you the random number function in a minute, but for now just assume it generates a floating point number between 0 and 1. And let's assume that in one case, a random number generator generates a uniform distribution, in another case it generates a normal distribution. So once that's done, I want to plot it. And all of you have looked at assignment 0 and have already generated a plot, I hope so. And I want to kind of show you, talk about that matplotlib library a bit. Python, you probably know matplotlib, right? Everybody knows matplotlib who has done a bit of Python work. The nice thing is you can wrap that in C++ easily and can use the same functionalities you know from matplotlib in our C++ codes. So I create a new figure with that size. I plot the histogram where the x-axis is my list of midpoints of the histogram, and the y-axis is a normalized data on those points. And now you understand why I expose these functions from the histogram, so I can just pass them to the plot function so I get what I need. And then I save my plot. So what you see here is a bunch of uniform distributed data for different amounts of attempts, for different amounts of random numbers, and a normal distribution. So you see the random number generator we get from C++ do a very good job at really providing statistical properties as we expect. So that was the whole point of this exercise, to show you these graphs, the statistical properties of the random numbers are really good. Just an aside with regard to the matplotlib header file, to show you some examples. It wraps the Python library matplotlib. The documentation is online, you can find it. I have pre-installed matplotlib.h on the Docker file for the assignments. As you have seen for assignment 0, you already have been using it essentially, even if you haven't done anything directly with it. And here's a minimal example. The actual namespace is matplotlib-cpp, but we give it a different name so that it's easier for us to write. Then we generate a vector of doubles, plot it, and save it. Done. Easy as that. A bit more complicated example shows you plotting 3 graphs. One sine, one a bit more complicated, a logarithmic graph, and so on, and shows you what you can do. You can specify that it should be red, it should be dotted, and all these things in a very similar way as you do that with Python. And if you look at the graph, you get that from the code that is on the slide. Just as some ideas what you can do with that library, because we will use that library over and over again for all the assignments for various things, and you might want to use it in the future for your own work. Okay, any questions so far? Then let's talk about Monte Carlo methods. So these Monte Carlo simulations are used whenever it's not feasible or impossible to compute the actual result, either analytically or using some iterative methods. So what you do, you use it especially for systems with very large number of independent variables, or for modeling phenomena that are significant, that have a large uncertainty in the input. Or you can use them in mathematics, in business. People use it in business to predict business evolution over time. Not sure how valid that is, but it's widely applied in business modeling, in risk modeling, and things like that. So what you do with Monte Carlo methods is you rely on repeatedly random sampling, and you pass that random number to a deterministic algorithm and collect the result. And you repeat that many, many times over. So let's do some examples. Let's assume I have a square of length 1, and I choose 2 points in that square, and I want to know what's the average length of those lines between the 2 points. Okay? Something which is the mathematicians have found out how to compute. We have a numeric and analytic solution. It's probably the solution of some integral. I'm not going to derive that for you, but this is the analytical solution for that. So that's the average length of the line inside that square is around 0.52 something something. Not interesting how that's done. If you're a mathematician, please feel free to prove that to yourself or whatever. What I want to do, I want to calculate that using Monte Carlo methods. So how do we do that? We repeat it a larger number of times. We get 2 random numbers which are in the range between 0 and 1. We compute the length between those 2 points. Well, 4 random numbers, right? X, Y, X, Y. So 2 points. We compute the length, accumulate the length, and in the end we divide by the number of attempts, and that should give us the average length of our lines we've got. Easy as that. So let's start to write that code. We define the random device and the random number generator globally. That's fine. We know they are thread safe, so we can share them between threads, and we will share them between threads, so we do a global variable. And then we define a function that I named getRandomNumber. And what it does, it produces a random number in the real floating point distribution between 0 and 1. Exactly what we want. And returns it by using the generator that is defined in the global namespace. Just a helper function for simplicity to make the code more readable. It squares the number it receives and returns it, so nothing special there. And here is the code. So we have a loop. We want to try it a larger number of times, in this case 10,000 times. We get 4 random numbers by calling our function, x, y, and xy. Then we calculate the length of the line between those just by squaring the difference and taking the square root. Nothing special. Accumulate the length and print the result by dividing the accumulated length by the number of attempts, and that gives us the average number of things. Our first Monte Carlo method. We simulate the length of the line inside a unit square. Okay, what's the error of that? How many attempts do we actually need? What do you think? How many attempts do we need to get a precision of, let's say, 10 to the minus 4? How often do I have to try that? Any suggestion? 1, 2, 3? A million? 100 million? Well, here's a graph. Just a table I collected, and you see that when I have, I don't know, 500 million attempts, we get very close to about 2 times 10 to the power of minus 5. So you see that at a certain point, it actually doesn't get much better. So you can use this kind of graph to assess, well, probably 10,000 attempts is probably correct, good enough for our purposes, right? Any questions so far? Very simple code. I just wanted to demonstrate that. Okay, second example. Anybody gambling? No? So the question is, would it be profitable given 24 rolls of 2 dice to bet against that there being 2 6s? In other words, will there be 2 6s when I throw 2 dice 24 times? Would anybody bet against that? So what is it? How would it be profitable given 24 rolls of 2 dice to have at least once 2 6s? So in other words, how large is the probability of getting 2 6s when I do it 24 times in a row? Anybody? Would you bet against it? Well, I know you're not gambling, but I wouldn't bet against it. But okay, how do we calculate that? Let's first calculate the real probability of that. What is the real probability of that? How do we calculate that? What's the probability with 1 dice to get a 6? 1/6, right? What's the probability with 2 dice to get 2 6s? 1 over 36, right? Now, in order to compute that, let me give you a hint that it's easier to compute the probability of not getting 2 6s than to compute the probability of getting 2 6s. So let's compute the probability of not getting 2 6s. What's the probability in one throw not to get 2 6s? 1 minus 1 over 36, so 35 over 36. So what's the probability of not getting 2 6s in 2 throws? Just multiply the two values. So in other words, the probability of not getting 2 6s in 24 throws is 35 over 36 to the power of 24, which is roughly 0.52, if I remember correctly. 0.51. And since we want to know what's the probability of actually getting to 6, we have to subtract that, and the real number is 0.49. And that means it's not profitable to bet against it, because you will lose in 51% of the cases. So the bank always wins, right? That's why they chose 24, because if you use 23 throws, you still can win. With 24, you can't win anymore. Okay, same logic. You do it n times. You get 24 pairs of random numbers. You look if there are 2 6s, count the wins, and in the end, you divide the number of wins by the number of attempts, and that gives you the probability. This time, we use an integer distribution between 1 and 6 because we want to simulate a dice. So we roll the dice twice in a loop that is executed 24 times. And if both of them are 6s, yay, we won. Otherwise, we just return false after 24 attempts. Easy as that. And then we call the function attempt to win in a loop and do that 10,000 times. And count how often did we actually win and how often did we lose. Okay? Okay, let's look at the graph again. As you can see, we get close to 49.1 after roughly 10,000 attempts, which is kind of interesting. So it seems to be a magic number when it comes to Monte Carlo, when you want to look at a certain error rate. And that is consistent across many Monte Carlo methods, that 10,000 is the first good guess when you want to do these things. At least when you want to achieve some stability, right? After that, you see it kind of flattens out and doesn't change more. It's still not correct and exact, right? And the error just goes up and down, but you get very close to where you want. Last example, estimate the value of pi. It's a well-known thing, and people use it normally to present Monte Carlo methods. How can you calculate pi using Monte Carlo? Well, it relies on the understanding that the area of a square of length 1 is 1, and the area of the inscribed circle is pi over 4, right? Because the area is pi times r squared, and r is 0.5, so the area is pi over 4. So what about if we generate points inside the unit square and count how many actually hit the circle and how many don't hit the circle? And that ratio of the two gives us pi. Okay? Because if you assume that the points are evenly distributed, they somehow represent the area of the thing they are hitting, obviously. So pi is 4 times the ratio of these two. And we say we can approximate the area pi by using n random samples and count the points inside the circle and multiply that by 4, and we get roughly pi. So just graphically represented for 10 attempts, 100 attempts, 1,000 attempts, you see that the number of points generated roughly kind of give you the ratio of the areas. Okay, so let's write that code. Same thing again. A loop where we do that 10,000 times. We get 2 random numbers because we want to have 1 point. We need an x and a y coordinate. We see if the sum of the squares of these 2 numbers is smaller than 1. We don't have to take the square root of that, right? We just want to, if the sum is smaller than 1, then the square root will be smaller than 1 as well, obviously. And count the number of hits, and in the end we just print the 4 times the number of hits divided by the number of attempts, and that gives us pi. Makes sense, right? So let's see how that works. Same thing. You see that we are getting close to pi, to about 1.5 times 10 to the power of -5 when we have 500 million attempts. And as before, it starts to become stable when we actually get beyond 10,000 attempts. Interesting observation. I can't explain that. It's just an empirical result I see over and over again in these things. Okay. So far, Monte Carlo. Now, you might imagine that 500 million or even more attempts when you have more complicated math might impose quite some execution time on these simulations. So what I would like to do, I would like to parallelize that. And we will see that parallelization is actually trivial in this case. And want to give you some steps what the caveats are when we parallelize things. But before we start doing that, what are the preconditions that we have to have in order to be able to parallelize things? What do you think? What do I need? And I have a problem, some computational problem. When can I parallelize that problem? What do I need for that? Well, first I need hardware that supports more than 1 core, right? Otherwise I can't parallelize it. If I have only 1 core, I can parallelize it, but I will not get any speed up because the execution will run on the same processor, so there will not be any benefit. The second thing is I need to have tasks that are independent of each other, that can run at the same time. If I don't have that, if I have interdependencies which sequentialize the sequence of steps anyway, then parallelization will not help me, obviously, because parallelization helps only when I have 2 tasks that can run on 2 different processors concurrently at the same time, squeezing the overall execution time that way. Okay. Before we start looking into that, I just give you the graph of what execution time do you get when you run this code I just showed you sequentially. So for 500 million points, it ran about 16 seconds. And you see it's a linear increase as expected, because we just repeat the thing over and over again, and each execution adds a certain amount of execution time. So we expect a linear, a complexity of 0.1, obviously. But just remember that number, 16 seconds, okay? Yeah. To be a bit more rigorous about the question of what do we need to parallelize something? This is a picture I will show you over and over again over the semester. Essentially, it tells you that in order to really parallelize a code, you have to go through 4 steps. You have to decompose the problem into tasks that can be run independently. You have to understand which of the pieces of your execution of your algorithm can run independently of other pieces. That's what we will do in a moment. Then you have to assign those tasks you have identified to parallel execution units. You have to say, okay, you go there, you go there, you go there, and then they can run in parallel. Once that's done, you have to establish what are the interdependencies between those tasks, because not always you have completely independent tasks. You might have interdependencies. You might have to do this first, and then you can spread out, and then you kind of have another dependency and so on. And last but not least, you have to map that into real hardware. You might have 100 tasks, but only 4 cores. How do you map that onto the execution? And which of these 100 tasks do you run first on your 4 processors you have available to you? Okay. Let's talk about that in detail. So computation of pi is what's called embarrassingly parallel. And it's called embarrassingly parallel because it's embarrassing for me to explain these simple things to you. Because in our case, parallelization is embarrassingly easy to do. Why is it easy to do? What are the tasks we have to run for pi? What is it we can isolate as a single task and we can distribute or spread out and parallelize? Well, the loop body, right? And the loop body of the attempts, each attempt is completely independent of any other attempt we do. That means that the loop body can be run in any sequence concurrently. It doesn't even matter that we maintain the sequence of the execution of the loop body. It's random anyway, right? So the decomposition is trivial because the loop iterations are independent and can run in any order or even concurrently. The assignment to the workers is equally trivial because we use HPX, and I will show you how that works. The orchestration is not necessary because there is no interdependency between the loop iterations, as we just established. So we don't have to consider that. And the mapping, again, we use HPX. Don't worry about that at this point. So all we have to do, we have to focus on the decomposition, and the decomposition is absolutely trivial. So let's do that in code. And I will show you how that works. OK. I took this sequential code and wrapped the body into what's called a lambda in C++. For now, whenever you see something that looks like a function and that has the square brackets in front of it, it's a function that doesn't have a name, nothing else. So you could call it ABC, you could call it DEF or whatever, but since we are lazy, we don't give it a name. We just say, OK, here's a function for you. And we encapsulated our loop body in a function. And that loop body takes one argument, which will be the sequence number of the iterations, which are not used in our case, but I just wanted to have it there anyway. And once we have that, we can use a facility from HPX, which is called for loop, which is essentially the same as a normal loop. You specify the begin, the end, the body. And it automatically increments the number by 1. So we don't even have to do the ++ n. Okay? So what we get here is a sequential implementation of this thing that uses HPX facilities but doesn't do any parallelization. It's a sequential code. You might ask, why the hell do I have to transform my nice loop body, my nice loop I already had, into something completely different with lambdas and with a function and with whatnot? Well, the answer is I add another argument. That's all I do. I add another argument to the first, as a first argument to my for loop, and that parallelizes the loop. So I don't have to worry about parallelization myself at all. I just tell HPX, please run this body in parallel somehow magically. I know it's safe to run that loop in any sequence, in concurrently, however you want. Combine loop iterations into one big chunk or whatever. Do that, and we are fine. OK? Yes, please.
What did we say to increment NC in parallel?
Well, that's the next slide. Look what pi we get, 1.03. So to answer your question, it's not safe, right? Well, we get a bit of speedup. And the speedup is not large, right? The blue line is a parallelized version, and it speeds up by about, I don't know, 10% or something. That's one problem. The other problem is that the number we compute is actually nonsense. And you probably already know what's going on. Let's have a look at the code again, and I will explain both problems to you. Why didn't it speed up? I ran it on my laptop. It was 4 cores. So we should see at least the speed up of 3 or 3.5 or something. So that's a problem, obviously. Doesn't work. HBX is broken. Create a ticket. Tell us. And the other problem is that the result is actually wrong. What are the problems? Well, the first problem, that the speedup is not there, relies on the fact that we have a multi-core machine. Each core has its own cache. And all this function is being run concurrently on all cores at the same time. That means that we have different threads of execution, and each thread of execution refers to NC separately. What happens when a thread refers to a variable? It reads the variable into its local cache, operates on the variable, and writes it back to the memory, right? So if I do that on 4 cores concurrently, each of the cores pulls the variable in its own cache. And that means when 2 threads do that, the variable is jumping back and forth between the caches of those threads. The more threads you have, the more overhead we create by doing that. So that explains why the parallelization doesn't work. Because that one variable is shared and creates a kind of contention point where all the threads have to access it and have to work with it. The problem why the result is wrong, well, let me take a sidestep. It's called a race condition. Simple question. I have 2 threads, 2 variables, both are initialized 0. Thread 1 assigns 1 to x, and thread 2 assigns 2 to y. What is x after the execution? 1, right? There's no question. It's always 1 because they don't interact. Let's make that a bit more complicated. One thread uses y plus 1 and assigns it to x, and the other thread assigns 2 to y, and then it multiplies y by 2. What are the results of that execution if both values start off with 0? It could be 1. What else? It could be 3. What else? Could be 5, right? So it's a race condition. And let's think about it. If this executes first before this starts executing, what do we get? We get x equal 1 because y starts at 0. Now let's assume this is run first, then this runs, and then the multiplication runs. X will be 3. And if these 2 things run first and then that runs, we get 5. So it's a very typical race condition. It's called a race condition, which we have to consider whenever we share a variable between threads. And in this case, y is shared between the 2 threads. Okay? And there are more complicated things going on behind the scenes, but this is kind of the idea. Race conditions are really, really dangerous and bad and difficult to find. And they're difficult to find because you never know which of the cases you get when you actually test it, right? Each time you test it, you get a different case. Okay, some relevant definitions. Synchronization. Whenever I talk about synchronization, I mean the coordination among threads. So how do we coordinate among threads? And that is usually related to shared data. Mutual exclusion is a term which I will use when I want to convey that I ensure that only one thread can do something at the time. So they are mutually excluded, right? Either this or that. Critical section is a piece of code that is guaranteed to be executed by one thread only at the time. Okay? Only one thread can do that by whatever means, and I will explain those means. And last but not least, a lock, or well, let's call it a mutex. In C++, it's called a mutex, is an object that allows us to establish a critical section. Because it is a flag only one thread can hold at a time. It's like a token that I can give to one of you, and only one of you can hold that token at any point in time. You can pass on the token to the other guy, but then you are not allowed to execute the code anymore that is related to that token. And a mutex is a type in C++ that can be used for that. So a mutex has two functions, which is they are called acquire and release. Acquire waits for the token to become available and gets a token. And acquire gives back the token and wakes up any other guy who waits on the token. So it's kind of a mechanism to block more than one thread to go forward, because the first thread acquires the lock, and all subsequent threads will have to wait at that point for the token to become available, for the lock to be available, before they can proceed. And we will use a special technique in C++, and that might start clarifying why I said last time that the most important feature in C++ is a destructor. Because what C++ does, it has a special type which is called lockguard, which is initialized from a mutex. And that lockguard will attempt to acquire the mutex in its constructor. So it will not proceed beyond the constructor if some other thread holds the mutex. And it will automatically release the token, the mutex, in its destructor. And the destructor is automatically called whenever the thing goes out of scope. So whenever the lockguard goes out of scope, which is at the closing brace of the surrounding block, it will give back the token and will wake up the next thread that might sit in its constructor and wait for the mutex to become available. That's why the destructor is so important, because as you see, I never call release on the mutex explicitly. It's happening behind the scenes whenever this object goes out of scope. Okay? So let's apply that knowledge to our code. It's the same code as before, except I define a mutex, and I use a lockguard inside that section, which protects the increment of that, our counter, from multiple threaded, from race conditions, because only one thread is allowed to go past the unique lock. And only when that thread has exited its block, the next thread can go there. So there will be always only one thread exactly that accesses NC. So this is our critical section, right? This piece of code, this block, from the constructor of the lock to the point when it goes out of scope, that is safe land. Nothing can happen there. Okay, what do we expect from the results? Anybody? Will it work? Will we get pi? Well, yeah, we get pi. What about the timing? How long will it take to do that? Ten times slower. And that's the usual experience I have when I start parallelizing things. I have a sequential code that works, I parallelize it, it's 10 times slower than before. Yay! Mission accomplished. Well, not quite. So why is that happening? Wait, yes?
The constant acquiring of the mutex.
Yes, yes. Well, it's one thing, the constant acquiring and releasing of the mutex, which is an atomic operation on its own. You have to talk to the scheduler to wake up other threads. So there's a lot of surroundings that are involved. And second, you again sequentialize the execution, right? You force all threads to go through a needle of the eye of a needle. So this is definitely not what we want. Mutices can be used very nicely in contexts where you have large blocks of code, you know, where this is not relevant. So in some cases, it's the only solution you actually have. But here it's a wrong solution because the amount of code we are protecting is so small. Okay, what else can we do? Any ideas? Come on, it's an assignment, it's a homework, you have to solve it. What would you do? Yes? That's a good solution. I will get to that, but there's something in between I want to show first. Okay? Any other ideas? But very good, yeah. That's the final solution, we will see. There is something which is called atomic operations, atomic variables. Atomic variables are guaranteed to be thread safe. The hardware ensures that atomic variables are thread safe. So I can safely increment an atomic int from several threads and it will work, because the hardware ensures that. Atomics use special special instructions from the core that are there to ensure atomicity of the operation. So the ++NC operation is atomic, which in the end means pull the value from the memory, increment it, and write it back. And all that process is completely atomic. It will succeed without anybody else being able to do anything to that variable in the meantime. Okay, so at least we got our pi back without protection, right? See, we don't protect it in any way except declaring the variable as being an atomic. So we get our pi back, but unfortunately, the execution, and it's a purple line, is roughly comparable to our very first version where we got the wrong result. Well, at least we got the fixed result, right? But the parallelization is still bad. It's still 10% only speed up on 4 cores, which is not what we want. Any idea why? Same explanation as we had in the first case. It's a shared variable. All threads pull into their own caches, and the poor variable has to jump in between the caches constantly, which creates a lot of overhead, because each movement from a variable from one processor to the cache of the other processor has to go through the external memory. And that means we pay the full price of the slow access to the external memory on each of those operations, which kills our performance. Questions about that so far? No? Okay. Well, let's do what you suggested. The best way of doing things is, why don't we give each thread its own counter and sum up the counters afterwards? Then we get the best of all worlds. We don't have any race condition on the counter because we guarantee that only one thread accesses a particular counter at a time. Each thread has its own counter, so they don't interfere. They don't have to jump between caches because the thread runs on the same core and it will use the counter that is local to that core in the local cache of that core. And in the end, we somehow magically sum up the values we got from the threads that were running. Well, luckily in HPX this is absolutely trivial, because all we do, we add a reduction object to the for loop, which is in this case a reduction plus on this variable, on the variable nc, which means please create one of those variables for each of the threads for me in the background and pass it as a second argument to the loop body. Please note we have to use a reference here because that counter lives somewhere in the loop implementation and we want to refer to that. In the first lecture I talked about references, briefly, but here just remember you have to use a reference here because that counter that is passed in lives inside the algorithm and we want to increment that one that the algorithm generates for us. And the algorithm makes sure that each of the threads gets its own counter. We don't care how that's done. It's magic. So the loop body now increments the local counter and not the global counter anymore. So there is no interference between the cores on that global counter. And when the loop finishes, it automatically sums up all the variables it has created and gives you the overall result and writes the overall result to that variable it was initialized from. Exactly what we want, exactly what we need. So what do you think the timing will be? We get pi correctly. What's the timing? What do you expect?
Much faster.
Yes? On my laptop, 4 cores, what do you expect in terms of speed up?
4 times.
Well, not quite. It runs on Docker and there's all kind of other things, and probably my email client was fetching email while I was doing that, so it's not, but we get speed up of more than 3. Right? So it's about 5 seconds compared to 16 seconds originally, which is acceptable. It's a good speed up. Okay, so as you see, parallelization on one hand is very simple if you have the correct tools to apply. And that for loop is a very powerful tool we have created just for this purpose. On the other hand, it can be tricky if you are not really, if you don't know what you're doing, if you don't understand how the architecture actually works in the background when you execute code. So you have to always be aware of the structure of your computer you're working on. Yes?
Does reduction take more space?
Sorry?
Space and memory.
Space and memory. Well, it will allocate one counter per thread, which is a bit more, right? One integer or one whatever. It will probably need a bit more space, yes? Well, the speedup is important, right? We do high performance computing, not low memory computing. So we don't care about, well, we care about memory, but memory is a second thought. It's a second criteria. The performance is an important part. Any questions about that? The assignment 1, which I will post on Monday, will not have any parallel code assignment in it, but plenty of opportunity to do it yourself. So if you feel that you want to play around with it, and one of the problems is actually a Monte Carlo problem there. The problem there will be if you have 30 people in a room, how large is the probability that 2 of them have the same birthday? Okay, very similar to the dice or to the others. Feel free to play around and try to do the parallelization yourself. And feel free to go beyond what the assignment actually asks of you by creating graphs, by doing an analysis, by explaining things, so that you really get a hands-on experience how these things work and what you have to pay attention to. Okay? The other thing I wanted to note, and we still have a couple of minutes here left, is that I really would like for you, in the context of this course, to work on a project in addition to the assignments. By project, I mean something you are interested in, and I will not tell you what to do, but for you to select a real problem you are interested in solving. And writing the code for that, doing some parallelization, possibly do distributed parallelization, as we will discuss in the second half of the course. So not use only one machine, but use 2 or 3 machines or 4 machines to parallelize things, to distribute that across a computing cluster. I will put some write-up together and we'll post it on the website, but I wanted to use this opportunity to kind of announce it, that I will do that. So you can start thinking about what you actually want to look at. Choose some scientific problem you're interested in doing, some integration problem, right? Some numerical integration, or some stencil code, or hydrodynamics, or anything that is interesting to you. N-body problems, right? Galaxy. What happens? Why is the galaxy evolving this way? You can easily do that with computation because each point has a mass and has a distance, which gives you, based on the gravity equation, what the interaction will be. You have some forces working there, so you can simulate how a body of, or a large set of bodies will evolve over time and what structures will be created and so on. So whatever you would like to choose is fine by me, as long as in the end you have a real problem, solve it, do some parallelization, possibly do distributed computing so that you get a hands-on experience and can apply everything we're talking about in one way or another. Start thinking about it. It will be very loose description. Essentially, go do it. Okay? If you have questions, need suggestions for that, or some ideas, I'd be happy to discuss that with you. Okay? And if that works out, we can use that as a final examination result. So you don't have any additional work, but do some hands-on work, which is much more important than me asking you, hey, how do you increment a number in C++, which is, yeah, right? So let's do it this way. Do a nice project over the whole rest of the semester, and you hand it in, and in the end, that's the final examination, okay? Is that acceptable to everybody? I see everybody nodding. That's good. Okay. Start thinking what you want to do. Thank you so much.